Okay, so we will be talking today about the gas behavior. Of the three states of matter, liquid, solid, and gas, the gas state is the one that has been studied the most and the one that is best understood. Okay, so a lot of the concepts that we will talk about today are not new to any of you. You know them. If I ask you to define a gas or to tell me the difference between water liquid and water vapor, let's say somebody walks in through that door from another planet and they really don't know what vapor water is. What is the difference between water vapor? What's this business that we call gas? What would you say to this being? How would you define a gas? Okay, we all know what water vapor is. Okay, that's what we teachers try to do. Explain things so that other people can relate to. What do you say? What would you say? What are some things that you would come up by starting? And let's throw some statements out and then we'll polish them until we get it all right. It's a state that has no definite shape, is what I'm hearing. Okay, so that means when I am in a state of no shape, when I'm out of shape, I am a gas? Not quite. So maybe not. Okay, so we begin throwing things out and polishing them. I'm out of shape and I'm still a solid. So what do we mean, really? What else can we add to it? Do the liquid state have shape? Do the solid state, does it have shape? Okay, so what do we mean by that? Just think of something like water liquid and water vapor, something that's very common to you. And I'm thinking, what? How do I differentiate liquid water? How do I explain to this being that honestly has no idea? Let's pretend I'm from another planet and I don't know what a gas, I don't know what vapor water is. What would you say to me? How would you explain the difference between liquid water and gas, vapor water? Gas has no volume of its own. It occupies the volume of the container, but what about the liquid? I have my water bottle with me, and if I put this water in a round container, it will occupy a round volume. So water doesn't have any volume either. Okay, so let's polish that one. We're getting warmer. It has to do with volume, it has to do with shape, but yes, I'm sorry, what did you say? Say that so loud so everybody can hear you. Like if you had lunch.
The particles are farther apart in the gas and the particles are closer.
Okay, she's saying that whatever is inside the container, let's say we're talking about water. The particles, meaning the molecules of water, are closer together in the liquid than what they are in the gas. And that means what? Am I breaking bonds? Am I breaking? Water has covalent bonds, right? We have V-shaped molecules. They have two covalent bonds, two lone pairs. It's polar. We know all kinds of things about water. When I get my liquid water and I heat it up and it turns into vapor, am I changing the composition? I form gas, hydrogen gas and oxygen gas. Is this what I'm doing? Let's try to visualize what I am hearing. Water, liquid, I heat it up. If I put an heat, meaning a triangle, on the arrow, is this what I'm forming? Hydrogen gas and oxygen gas? These are gases and this is liquid. The L stands for liquid, the G stands for gases. Is this what happens when I heat up water? Is that true? I'm hearing yes and I'm hearing no. No. Yes, why? No, why? I'm after the whys. this would happen not if I heat it, but if I maybe electrolyze water. Electrolysis, this would happen. But if I heat up water, if I just plain heat it, what am I forming? If all I have is a container, I'm going to make tea, and I have water inside a teapot, and I'm heating it up in my stove. What am I forming after the arrow? Okay, so my water molecules are given heat energy. I'm giving them heat, and they are going to move faster, and they are going to spread apart. But what am I forming? Water, gas. Okay, so this top change, that's a chemical change. Chemical change. I start with A, water, I end up with something new, hydrogen gas, oxygen gas. That's not what happens when I change a state. When I go from liquid water and I freeze it, I put it in the freezer, I go from liquid water to solid water, an ice cube. Or if I heat it up, I go from liquid water to gas water, but I still have H2O. Same molecule. But it is, as you said, the distance between the molecules are so different. Okay? To the point that if I have water vapor in a container that's 1 liter, the volume of the gas would be 1 liter. If I shrink that to 250 milliliters, then the volume of the gas is 250 milliliters. If I expand that to 5 liters, then the volume of the gas is 5 liters. So gas occupy the entire volume of the container. Okay, in the case of a solid, it has its own fixed volume. Okay, so in order for us to talk about gases, we have already used a variable volume to address its behavior. We threw in the fact that we were heating it up. So temperature is another variable that is needed in order for us to understand the gas behavior. We measure the volume in what units? Milliliters, or liters, or quarts, or gallons. Those are all units that are no longer new for us, right? Milliliters, liters could be units to express the volume. So I could have 1 liter of a gas or 500 milliliters of a gas. And when I change my temperature, I'm heating it up or I'm cooling it down. That's another important variable. In this chapter, we're only going to use what units? Kelvin. How do we get to Kelvin if we're in Celsius? Kelvin is Celsius plus 273. Okay, so whatever we've said in the past, we cannot forget. We're still using it. What about if we don't have the temperature in we have it in Celsius, and we want or we have it in Fahrenheit or Celsius. What's the conversion between those two? Fahrenheit was what? 1.8 times Celsius plus 32. So if you're in Celsius, if you're in Fahrenheit, you need to convert to Celsius, and then from Celsius you need to convert to Kelvin. So bottom line, you must land in Kelvin. In this chapter, we cannot work in Celsius, we cannot work in Fahrenheit, and we know how to do this, correct? We're remembering module 1. Okay, the amount of water, we're talking about vapor, water in a container. The amount is going to be measured, and we chemists love the term moles. Okay, so moles talks about the amount, and that's another variable that we need to consider in the understanding of the gas behavior. And finally, the other variable that you talked about, molecules were hitting each other faster when I heat it up, and there are higher pressures, is pressure. Okay, so let's make a pause here and make sure that we understand this last variable. Pressure. if I have mercury. Mercury is a metal. What state of matter is mercury? Liquid. If I have a pool of mercury, mercury is liquid. I have it in a container. And in this container, I have this pool of mercury, and it's at sea level. Miami, anywhere you go, it's pretty much sea level. This is flat as a pancake. I come from Venezuela, and we have beautiful mountains, and I couldn't believe how flat. You drive and drive and drive, and the whole Florida is like, it's a while in order for you to see a little hill. Maybe if you go on top of 836 next to Jackson Memorial, you get a little higher. But every place else is pretty flat, pretty sea level. Okay, so the pressure that the atmosphere is exerting on this pool of mercury is going to be totally different than if I go below sea level or if I go above sea level. If I go on top of a mountain and I have my little container with mercury, the pressure up there is going to be totally different than the pressure down here. Yes? That concept is not foreign to anybody. Let's say I take a piece of glass tubing and I invert it, and I measure the height that this mercury is going to give me at sea level. If I measure it with a ruler, and we've seen this ruler many times, this is a meter stick. The distance, very dirty meter stick, the distance between my right and left index is 760 millimeters. This distance between this right index to this left index. If I put that glass tubing on top of my mercury pool, that distance is 760 millimeters of mercury. And my pressure at sea level is 1 atmosphere. So the pressure that I have at sea level is 1 atmosphere. If I take that same setup and I go on top of a mountain, is my pressure going to be 1 atmosphere? Is my pressure going to be 760 millimeters of mercury, which, by the way, is identical to 760 torrs. So torrs and milliliters of mercury are the same thing. And you have conversion factors here. Is my pressure up there going to be higher or lower? I hear higher, I hear lower. So let's not go on top of a mountain, let's go underneath sea level. This is sea level. And now I'm going underneath sea level. Okay, I have what? More pressure down here? We've all gone swimming in the ocean. We've all, if that's not true, then we've all gone, we're in Miami. So we've seen a pool someplace. Maybe we've gone inside there. And what happens when you go underneath the water? Do you have a greater pressure or less pressure? Oh, and now I hear nothing but greater. Okay, so that's what you do. When you don't know an answer, you go elsewhere. You figure out a way out. You find a back door, and there's always one. You just need to find it. So if there's a greater pressure down here, and because I have a heck of a lot more, the pressure up here must be what? Less. So the higher that I go, I can go less and less torrs. Okay, so the pressure is a variable that will affect the gas behavior. And we need to convert from one unit to the other one. And we know how to do that seamlessly because Module 1 is so very well understood. Yeah? If we look at example A, and I ask you to, okay, so the lower we go, the greater the pressure. So down here we can talk about 2 atmospheres, 3 atmospheres, whatever. It depends how low you want to go. If I want to convert example A 1.7 atmospheres into torrs, or into millimeters of mercury. How do I do that? Do we remember Module 1? We didn't forget Module 1, right? No. And how do I convert that into torrs? I put what? 760 torrs, very good, on the top, very good. And what? 1 atmosphere on the bottom, so that my units, atmospheres, cancel. Does this sound familiar? Have we heard this before? Are we doing anything new? No. We did it with inches and centimeters and gallons and milliliters and quarts, and now we're doing it with atmospheres and torrs. But we got a winning strategy. We got factor labels coming to our rescue. And our answer is going to be correct because our units canceled. And if I wanted millimeters of mercury, what is that? The same amount, because millimeters of mercury and torrs are the same thing. 760 torrs is 760 millimeters of mercury. 1 millimeter of mercury is 1 torr. Okay, so if I ask you to convert atmospheres to torrs or to millimeters of mercury, we just go back to Module 1 and do the exact same strategy. Yes? No, I define this. I define my conversion. Just like I define 100 cents in a dollar or 24 hours in 1 day, I'm saying there's in 1 atmosphere what? 760 millimeters of mercury. Okay, so if I'm after atmospheres, I would have to flip it all. If I start you with torrs and I want atmospheres, it would have been the exact opposite. Okay? Any other questions? Okay, so you do example B and C and all the other ones. I walk you through what your homework is. You get your homework done. In order for us to understand the gas behavior, we are going to take a tour through history, and we are going to address great names like Boyle and Charles and Gay-Lussac, because these guys in the 1800s, a long time ago, studied gases. But their findings are so intuitive and so simple that it's really your name that should be here. These guys just beat you to it because they were around a little bit earlier than our generation. But once we find out what they did, and you're going to tell me what they did in a minute, we're going to outline these 3 laws and call it a combined law. So this is hopefully the whole chapter in a nutshell. And after we do the combined law, we're going to do a couple other laws like ideal gas law and Dalton's law, and hopefully we'll make it to Henry's law. Okay, so this is Module 8 in a nutshell, starting with Boyle's law. Okay, and what we're doing is we're going to take these 4 variables and we're going to take 2 variables at a time. Like we're going to start with volume and pressure and change one and see how the other one's affecting. And the other variables like temperature and amount are going to be constant. And then once we study pressure and volume relationships, then we're going to take temperature and volume and study those, keeping pressure and amount together and see how they affect each other. And then we're going to continue to do that until we get all the variables addressed and all the variables understood in an effort to understand the gas behavior. Okay, so my very first 2 variables are volume and pressure. Dependency on these 2. And I am going to take the example of a gas trapped in a container with a movable piston. So let's say in here I have a gas, and this volume of this gas is 5 liters. And this gas is at sea level. So I am right at sea level. And the pressure at sea level is, in atmospheres, what is it? 760 or 1 atmosphere. 760 torrs equals 760 millimeters of mercury equals 1 atmosphere. So I'm at sea level. But this piston moves, and these gas molecules that I have in here are going to be now going to change because I am going to lower my piston, and instead of being there 5 liters, I'm going to bring it down to half of it. I only knew why it does that. It would be so great. So my second volume, I squished this down. I moved my piston down. It's half of what I originally had. I had a volume of 5 liters. What's half of 5? 2.5 liters. Now let me ask you something. If my temperature and my amount not changing, temperature and amount are constant. Okay, so I'm not heating this up, I'm not removing gas from it, I'm not adding gas. So whatever molecules of gas I had there, I still have. Is my pressure going to be the same? My volume is decreasing by a factor of 2. Is my pressure going to remain at 1 atmosphere? No. So I'm going to have a new pressure, which I'm going to call P2. Is P2, my new pressure, going to be higher, or is it going to be lower than my original pressure? It's going to be higher, right? If there's 100 of you in this room, and then all of a sudden we move to a little tiny cubicle, the pressure is not going to be the same. And we're not even gas. So our pressure is going to be a heck of a lot higher. So if the volume decreases and I have the exact same number of molecules, my pressure will go up. My volume is going down. It's decreasing. Arrow down means decreasing. That means that my pressure is doing what? It's going up. It's increasing. Now, if my volume is going down by a factor of 2, what is my pressure going to do? It's going to go up by a factor of? So what is my final pressure, guys? 2 ATMs. Congratulations. You just defined Boyle's law. So your name should be there. Okay, Boyle just beat you to it. All he did was took this and made it into a mathematical equation. You are saying that volume and pressure are inversely related. If one goes up, the other one goes down. If one goes down, the other one goes up. Okay, so volume and pressure are inversely proportional. How do we say that in a mathematical way? Okay, so I need now to make a general statement to make a law. Okay, so people went to the lab, did this many, many times. Scientific method, you repeated it, and every time the same findings. Volume went down, pressure went up. Volume went up, pressure went down when the temperature and the amount wasn't changing. How do we say that? V1, what? Speak louder, like we had lunch. V1, P1, yes? Equals V2, P2. Wonderful. So what did you do? You multiply 5 times 1. V1 is 5 liters. P1 is 1 atmosphere, correct? And that gave you what? 5 times 1 is? 5. And that's the same as 2.5 times 2. So your second volume is 2.5 liters. And your second pressure is 2 atmospheres. So you said that 5 equals 5. Wonderful statement. Except this takes you places. And this is Boyle's law. And we'll just give him credit because he did it first before we did it. Okay, so all it's saying is that volume and pressure are inversely proportional. Are we okay with that? Yes? Questions there? Okay, so we took 2 variables. Now we're taking another 2. Let's take volume and temperature. Let's examine volume and temperature. Okay, so we first examine volume and pressure. Now we're examining volume and temperature. And now we're going to keep get out of here, keeping pressure and amount constant. Let's imagine we have the same gas, and we have this at a temperature of 300 K. We're using Kelvin. Our original temperature is 300 Kelvin. And I have 2 liters of a gas. Okay? And I am going to change my conditions, and I am going to heat it up. Okay, so I'm going to heat it up. I put some heating element underneath. And I have a movable piston. So my volume is going to change. Let's say my temperature is going to take me all the way up to double my original. What's double 300? 600. So I'm going to go to 600 K. Is my volume going to go up, or is my volume going to go down if I'm heating this gas? The volume is going to go up. Okay, I'm heating this thing up, and the pressure is not changing. The pressure cannot change because my pressure is constant. Okay? So my pressure is not changing. My temperature, I'm heating it and heating it and heating it. And what happens when you heat something? This is how helium balloons, how do you call them? Hot air balloons, thank you, work. Okay, you just heat up the helium inside them, and this thing goes up. Okay, they expand the helium, and that changes the density. So my volume is going to go up. Now, if my temperature is going to go up by a factor of 2, what's my volume going to do? It's going to go up by a factor of 2. So what's my final volume going to be, guys? Congratulations, guys. You just did. So if this was 2 liters, it's not going to stay at 2 liters. It's going to go up here to 4 liters. This is Charles' law. Okay, so if my temperature increases, arrow up means it increases, my volume does what? My volume also increases. Temperature is a very friendly variable. Doesn't rock the boat. One goes up, the other one goes up. Same thing for pressure. If pressure is considered as you increase your temperature, keeping your volume constant, if you increase your temperature, your pressure goes up. Okay? And we intuitively see that. Like in a very cold day, I'm not a gas, but my rings kind of fall off my finger. I kind of shrink. Volume decreases when the temperature goes down. When it's really hot, I can't even get my rings off. I'm so blown up. And I'm not a gas. Okay? Okay, so temperature increases, volume increases. If temperature decreases, volume what? Decreases. And we say that volume and temperature are directly proportional. Directly proportional. How do we say that mathematically? How do we say what we did? And this is the big deal. You told me the answers. Whoa. No, don't do this, please. Okay. How do we say what you told me here in a mathematical expression? I'm sorry, I couldn't hear. V1 over what? over T1, is that what you said? Equals what? V2 over T2. Let's check it. What was V1? You tell me. V1 was 2 liters and T1 was 300. So I'm going to put 2 liters over 300, okay, equals what? What's V2? 4 liters over what? 600. Is that true? If I divide this by 2 and this by 2, what do I get? A 2 to 3. So yes, 2 over 300 is 2 over 300. Okay, so that was Charles' law. V1 over T1 equals V2 over T2. And as I said, temperature and pressure could also be examined, and they're also very intuitively seen. If I have a gas and I'm heating it up and my volume is now fixed, I'm not changing volume or amount, I'm heating up a gas, getting it hotter and hotter and hotter, what happens to the pressure in there? It gets what? Higher and higher and higher. Okay, that's how we started the discussion. Okay, the molecules are going to collide faster and faster, and the pressure increases. So if we combine all these findings, that one was Gay-Lussac. Gay-Lussac, it says the same thing. P1 over T1 equals P2 over T2, meaning if your temperature increases, your pressure increases at constant volume and amount. So if we put all these together, Gay-Lussac together with Charles, together with Boyle's, we have the big one, combined law. And what's the combined law going to say? V1 P1 over T1 equals what? V2 P2 over T2. So if I have the same temperature, this disappears. What do I have? Boyle's law. Let me write it back on there. Okay, so if it's the same temperature, T1 equals T2, they cancel, and that's Boyle. If I have the same pressure, if P1 equals P2, and I get rid of this, P1, and I get rid of this, P2, what do I get? Right here, Charles. If V1 equals V2, and I'm now at Gay-Lussac, then I have all three relationships together. Okay, so let's give the whole thing in yellow. V1 P1 over T1 is V2 P2 over T2, and that's the combined law. That's going to be our first law. Do one example, or do I leave that for homework? I can't hear you. Do one. Okay. Page 138, problem 2E. It's usually the one you ask me. Has most numbers and all of the examples and give you there. What would be the new volume of 5 liters of a gas? So my strategy is to label what's V1, what's V2. So I need V1, I need V2, I need P1, I need P2, I need T1, and I need T2. What would be the new volume if I originally have 5 liters of a gas? So where do I put 5 liters? On V1. Very good. What would be the new volume? I don't know what the new volume is. If its pressure decreases from 2 atmospheres to 1. So where do I put 2 atmospheres? P1. I started in 2 atmospheres and it goes down to 1. And the volume and the temperature triples from 100 to 300. So my original temperature is 100 K and my final temperature is 300 K. This I can do mathematically. And since I know you don't exactly love algebra and math, some of you anyways. We're going to do it both mathematically and intuitively, because you can do this. You know this. You will give credit to everything you know. Okay, so if my pressure is going down, and I'm looking at P1, 2 atmospheres, P2, my pressure is going down. What's my volume going to do? It's going to go up or going to go down? It's going to go up, because volume and pressure are inversely related. If my pressure is going down by a factor of 2, from 2 to 1, in your test, I am not going to give you round numbers, 2 and 1 and 4 and 3. I'm going to give you 342, whatever. Okay, it doesn't matter. If it's increasing by a factor of 2, it increases by a factor of 2. Okay, and you can divide the two numbers given. But in here, you can do it in your head. 2 atmospheres. To begin with, it goes down to 1 atmosphere. So I'm cutting it in half. I'm going down by a factor of 2. So what's my volume going to do? It's going to go up by a factor of 2. So if all I do is change my pressure, my original volume is 5 liters, my final volume would have been what? 10 liters. 5 times 2 is 10. Yes? But on top of that, keep that 10 liters in your head. On top of that, I changed my temperature. Those 10 liters are 100 K. And now I'm going to heat it up threefold. I'm going to triple the temperature from 100 K to 300 K. Okay, so I'm doing in my head 300 over 100. Okay, and if they're not whole numbers, you just divide them anyways. So I'm going up by a factor of 3, and my temperature is going up by a factor of 3. So my volume is going to do what? Up or down? Up by a factor of 3. So instead of being 10, it's going to be what? So my answer is going to be 30. Okay? It's that easy. This chapter is so intuitive. You know this stuff. Okay? Your name should have been there. Let's do it mathematically. V1, P1 over, I'm plugging in here. V1, P1 over T1 is V2, P2 over T2. Over T1 equals V2, which I don't know, P2, which I do know, over T2, which is 300. I solve for V2, so I'm going to have 5 liters, 2 atmospheres, over 1 atmosphere, 300 K over 100 K. So if you do it mathematically, you still get the same answer. Okay, so I'm giving you 2 methods. Either use the concepts, and volume and pressure are inversely related, and temperature and volume are directly related, and get your answer, or plug it in your equation and get the same answer. All right? Let's move to a mixture of gases. Let's look at Dalton's law. And again, it's Dalton just because he beat us to it. Otherwise, it wouldn't have been him. He studied a mixture of gases. So now I have a container, and in this container I have gas A, and gas A has a pressure of 100 torrs, and maybe gas A is helium. And I also have in there gas B, and gas B is krypton. It's 50 torrs. And I also have in there gas C, and gas C, tell me another gas. Neon. And this guy is 200 torrs. And C is in there too. And I ask you, what would be the pressure, the total pressure inside this container? What do you think? What's P total? And how do you get that answer? That's how intuitive this is. That is the correct answer. 150 plus 200 is 450. So all you did was add all this. So now make it a law. Now make it a general statement. What did you say? I'm sorry? 350, thank you. What is the general statement going to be? Somebody needs to know how to add. PT equals P1 plus P2 plus P3 plus P4 plus P whatever. Because they could have many more. But in words. Let's put it in words. The tough one. The words are the ones that always get us. In a mixture of gases. In a mixture of gases. What? The what? Total pressure equals what? Equals the sum, yes, say that. The sum of the individual partial pressures. So simple, not a big deal. If I have two gases, A and B, and the sum of the two pressures is 500 torrs, and I know that pressure of gas A is 200 torrs, and I ask you, what's the pressure of gas B? Why is it 300? What did you do? You subtracted 500 minus 200. So don't ask me, do I always add? No, I don't always add. I always use the concept, and this is the concept. I do whatever I need to do depending on the question. I could add, I could subtract, or I could do whatever. Not so bad? Are we all okay so far? Any questions so far? Okay, so let's do ideal gas law. Ideal gas law. Ideal gas law maybe was something you studied in high school. It has a ring to it. Did anybody study ideal gas law in high school? What does it say? Ideal gas law is? Very good. PV equals nRT. It kind of has a ring to it. PV equals nRT. If you've never heard of it, you just repeat it many times today and it'll sink right in. It has kind of like a nice ring to it. Where P stands for pressure, V stands for volume, N stands for moles, amount. T stands for temperature, and R is the universal ideal gas law constant. I am going to solve for R. PV over what? NT. Very good. R is a constant. Okay? And I'll just tell you, I need to get credit to Avogadro. I don't think we could move through without it. Avogadro's, good old Avogadro, the one that came up with 6.02 times 10 to the 23rd, did lots of studies in science and great findings for us. He found out, this is Avogadro's law. Just squeezing that in just to give him credit, because this guy really needs credit in the gas law chapter. Avogadro found that if you have 1 mole of a gas, so under N, I'm going to put 1 mole. At standard temperature and pressure, meaning at a temperature of 273 Kelvin, standard temperature is 273 Kelvin, and standard pressure is 1 atmosphere. The volume that it occupies never changed. It was always 22.4 liters. So if you multiply 1 times 22.4, divide by 1 by 273, you get the value of R. So R could be found, and it's 0.0821. The units are liter atmospheres per degree Kelvin mole. Okay, this is not in your book, but I just needed to throw it in there because it's like heresy to talk about gases and not give him credit. No, this is how we're going to use ideal gas law. We're always going to find that back door, that easy way out. Okay, that's the method in this course, in my style of teaching anyways. I will ask you questions like example F. At constant temperature, if the number of moles of a gas increases, the volume of a gas will. Okay, and that's the kind of lingo that you're going to get. So I'm not going to give you numbers in there. But bottom line, if we know the expression for ideal gas law, if we need to know PV equals nRT, the equal sign is separating variables like pressure and volume. And we said that pressure and volume are inversely related. If one goes up, the other one goes down. And volume and temperature are at two different sides of the equal sign, yes? So I'm looking at the equal sign. Volume is in one side of the equal sign, temperature is in the other side of the equal sign. And what happens? If temperature goes up, what happens to the volume? It goes up. Temperature and pressure are at opposite sides of the equal sign. If temperature goes up, what happens to the pressure? It goes up. Okay? Let's look at things like volume and amount. I'm sure you've blown up a balloon someplace down. You went to somebody's birthday party, maybe your own. And you got a balloon that was really squished, and you put air, and more air, and more air. And what's happening to the volume of this balloon? As we put more and more amount of air, it increases. Okay, so if you're at opposite sides, the more gas that you put in a balloon, the greater, the bigger the balloon gets. Okay, so this is that intuitive. If you are at opposite sides of the equal sign, if this goes up, this is going up. If you're on the same side of the equal sign, if this goes up, this will go down. If N goes down, temperature will go up. Okay, so at the same side of the equal sign, one goes up, the other one goes down. Opposite sides of the equal sign, one goes up, the other one goes up. One goes down, the other one goes down. Okay? There's nobody in this room that couldn't handle that. So with that thought, let's do example F. Example F. At constant temperature, if the number of moles, N, increases. If the number of moles of a gas increases, N is going up. I'm asking you, is the volume going to do what? What is the volume going to do? N is here, volume is here, it is going to also increase. What if I would have asked you, if the number of moles goes up, what happens to the pressure? Pressure and amount, N and P, if it also goes up. If there are opposite signs, okay? If I'm putting, now I don't have a balloon that can expand. Now I have the same sealed container. Okay, so I'm blowing air into here. And I'm going to add more and more air. And this thing is not going to expand. What's going to happen to the pressure in there? It's going to increase. So if N goes up, if the amount goes up, the pressure also goes up. Because they're at opposite signs. Okay, if I would have said, if I heat up a gas, what happens to the volume? It goes up. Okay, so if I'm at opposite sides, they're directly related. That's how we're going to use ideal gas law. Simple enough? Not so bad? And I still have a minute or so for Henry's law? Yes. Where's the attendance? Somebody loved my attendance sheet. But it's being passed around, and we have like, what, 5 minutes or so? So pass it fast, please. Okay, Henry's law is so simple, it's like an insult to your intelligence. This chapter is very intuitive. Henry's law talks about what happens when you consider pressure and concentration of a gas in a solution. Okay, everybody here drinks soda. We're terrible. We usually do stuff that we shouldn't do, and if you don't drink it, somebody else that you know probably does. What happens if you open a can of soda or a bottle of soda? It fizzes, right? Inside a can of soda, the pressure in there is like 5 atmospheres, 5.5 atmospheres. And what they're doing is putting a lot of pressure so the carbonation, the CO2 molecules, CO2 is a gas, gets inside the liquid. Okay, so the CO2 is your solute and your whole solution is your soda. Okay, the greater the pressure, the greater the amount of carbonation in there. Okay, so as pressure goes up, the concentration of solute in that solution goes up. What happens when you open the can and you leave it out and you forgot to drink it and then you come back 5 hours later? It's pretty flat, right? So once I open it, my pressure outside, we're in Miami. What's the pressure outside? 1 atmosphere. So if my, who needs it? If my pressure is going down, what happens to the amount of carbon dioxide in there? It went away and concentration went down. Okay, so it's telling you, Henry's law, drink your sodas right after you open them if you want them to taste the way that they're intended to be. Maybe you like them flat. Maybe you want to do that. But that's Henry's law. Now tell me a mathematical equation, just to close this whole lecture, that says that if pressure goes up, concentration goes up. And if pressure goes down, concentration goes down. What did we say? P1 over C1, P equals P2 over C2. Okay, so if you're saying that they're directly related, pressure and concentration are directly related, their ratio is constant. When you're saying that two variables are inversely related, if one goes up, the other one goes down, their product is constant. Not so bad? This is the gas behavior in a nutshell. Up to here is your test. Please go to the web under test 2, print each and every topic, and pretend your test is Tuesday, and then on Tuesday you'll bring me your questions. Have a great day.